floating, levitating above a material like magic. It almost defies gravity.
Yeah, it's a pretty striking image.
And the science behind that. That's what we're diving into today. It's been a kind of holy grail for physicists for, well, over a century now.
Absolutely. We're talking about room temperature superconductivity, RTS.
Right, an RTS. So maybe we should quickly unpack what superconductivity actually is.
Good idea. So it's a quantum thing, really.
Yeah.
Below a certain temperature, a critical temperature, materials do two amazing things.
Okay, what's the first one?
First, their electrical resistance drops to absolutely zero. Nothing. Nada.
Zero. Like electricity flows forever, no energy loss at all.
Exactly. Totally unlike, say, copper wire, which always heats up, wastes energy.
Okay, zero resistance. What's the second thing?
The second hallmark is that they actively push magnetic fields out from their insides. It's called the Meissner effect, or Meissner-Ochsenfeld effect, technically.
Ah, so that's the levitation part. The magnet floats because the superconductor is pushing its field away.
Precisely. And getting this to happen at room temperature, well, that's the dream.
Because the impact would be huge, right? Lossless power.
Oh, enormous. Imagine power transmission with no waste. And think about MRI machines, much stronger, cheaper, more accessible.
Maglev trains floating silently.
Definitely. Whole new transportation systems, and even big leaps in quantum computing.
It really does sound like science fiction.
It does. But the research landscape today is interesting. There's a real split.
How so?
Well, on one hand, you've got solid, verified science, especially with materials under really high pressure. We know superconductivity is getting closer to room temperature there.
Okay, the high pressure stuff. What's the other hand?
The other hand is, well, a lot of recent headlines. Big splashy claims about achieving this at normal pressures, ambient conditions.
Ah, I think I know some of the ones you mean.
Yeah, and unfortunately, those claims haven't really held up under scrutiny. They've failed verification.
So you've got proven progress under extreme conditions, and then these controversies, let's say, at ambient pressure.
Exactly. It's a duality. What's fascinating here is we need to explore both the triumphs and the cautionary tales.
Right. So the mission for this deep dive is to sort through all that, figure out what's real, what's maybe hype, and what's genuinely moving the needle in this whole quest.
That's the plan. Extract the key insights from all the recent developments, help you understand the science behind the headlines.
Okay, let's do it. Where do we start? The basic theory.
Makes sense. The foundation was really laid back in 1957. Bardeen, Cooper, and Schrieffer. BCS theory.
BCS. That was the first real explanation for how this even works microscopically, wasn't it?
It was. And the core idea was pretty wild for its time. It involved electrons pairing up.
Wait, electrons? But they repel each other, right? Negative charges push apart.
They do. But Cooper figured out that in the quantum environment of a crystal lattice, electrons can form pairs, Cooper pairs. Well, the simplest mechanism, the one BCS focused on, involves the lattice itself. Imagine one electron moving through. It slightly distorts the lattice of atoms around it, creating a little region of positive charge density.
Okay.
And that slight positive distortion can then attract another electron a short time later. It's like the first electron leaves awake and the second electron surfs it.
So the lattice vibrations, the phonons, act like a sort of glue.
Exactly. The electron-phonon interaction is the glue in conventional superconductors. And these pairs, they behave very differently from single electrons. They act like bosons.
Bosons, meaning they can all pile into the exact same quantum state.
Precisely. They condense into this single coherent state. And because they're all acting as one, they flow without scattering off imperfections or vibrations. No resistance.
And that leads to the energy gap you hear about.
Yes, the pairing creates an energy gap. Basically, it costs energy to break a pair apart, which suppresses the usual scattering mechanisms that cause resistance.
Okay, so Cooper pairs, phonon glue, energy gap, zero resistance. What about the Meissner effect, the magnet thing?
That also comes from this coherent state. The paired electrons can set up persistent electrical currents right at the surface of the material.
Surface currents.
And these currents perfectly cancel out any external magnetic field trying to get inside, so the field gets expelled.
Wow. Okay. And they knew this phonon idea was right because of the isotope effect.
That was key evidence. If you change the mass of the atoms in the lattice, use a heavier isotope of the same element, the vibration frequencies change.
Right. Heavier atoms vibrate slower.
And slower vibrations mean weaker pairing glue, so the critical temperature, Tc, goes down. BCS theory predicted exactly how Tc should depend on the isotope mass, and experiments confirmed it beautifully for many materials.
So BCS theory was a huge success. But then things got stuck for a while. I remember hearing about the 40K wall.
Yeah, for decades, it really seemed like this phonon mechanism had a natural limit. Based on typical lattice vibration frequencies and coupling strengths, calculations suggested you probably couldn't get TC much above 30 or maybe 40 Kelvin, minus 233 Celsius. Still very, very cold.
And experiments seem to back that up.
For a long time, yes. The highest known TC hovered around 23K for about a decade before 1986. It felt like a fundamental ceiling imposed by the theory.
But then 1986 happened. The cuprets.
Exactly. Bednorz and Miller discovered superconductivity in a copper oxide material, a cupret, around 35K. And very quickly after that, Paul Chu and his group found YBCO yttrium barium copper oxide.
And YBCO's TC was?
93 Kelvin. Suddenly, way, way above that supposed 40K wall.
93K, that's above the boiling point of liquid nitrogen, right? 77K.
Yes. That was a monumental practical breakthrough. Suddenly, you could cool superconductors with cheap, readily available liquid nitrogen instead of expensive, difficult liquid helium.
So the cuprets didn't just break the temperature record, they shattered the theoretical paradigm.
They really did. It proved that while the core ideas of BCS electron pairing and energy gap were likely still valid, the mechanism, the pairing glue, didn't have to be phonons.
It opened the door to unconventional superconductivity.
Absolutely. It forced everyone to think, if not phonons, what else could be pairing up electrons at these much higher temperatures? That question really launched a whole new era of research.
Okay, so that's one path looking for new mechanisms beyond phonons, like in the cuprets. But you mentioned another path, the high-pressure one, that sort of stuck with the phonon idea but pushed it.
That's right. People went back to the basic BCS ideas and thought, how can we maximize the phonon energy and the coupling? And the answer pointed towards hydrogen.
Hydrogen. Just plain hydrogen.
Well, the prediction, going back to Neil Ashcroft, was that if you could squeeze hydrogen enough to make it metallic, it should be a room temperature superconductor.
Why hydrogen?
Because it's the lightest element. Its atoms vibrate at incredibly high frequencies. Higher frequency phonons, according to BCS, generally mean higher TC.
Makes sense. But metallic hydrogen needs insane pressure.
Insane is the word. Something like 500 gigapascals, 5 million atmospheres. Just incredibly difficult to achieve and sustain, especially for measurements.
Too. How to get around that?
Ashcroft had another brilliant idea around 2004. Chemical pre-compression. Don't use pure hydrogen. Instead, embed hydrogen atoms inside the crystal lattice of another element.
Okay. How does that help?
The chemical bonds with the other element basically squeeze the hydrogen atoms together, creating enormous internal pressure. This could potentially stabilize a metallic hydrogen-like structure at much lower external pressures applied in the lab.
Like using chemistry to do some of the squeezing work for you.
Exactly. It provided a concrete theoretical roadmap. Look for hydrogen-rich compounds, hydrides, and squeeze them.
And this roadmap actually led somewhere.
It led to spectacular results. First big breakthrough was in 2015. Sulfur hydride, HS.
What did they find?
Superconductivity at 203 Kelvin. That's minus 70 degrees Celsius. Still cold, but dramatically higher than anything seen before. It needed 155 gigapascals, though.
Still huge pressure, but a massive jump in temperature. Proof of concept.
Absolutely, and it really ignited the field. Then, in 2019, came lanthanum hydride, specifically LARA.
And lanthanum decahydride, and its TT?
Around 250 to 260 Kelvin. That's minus 13 to minus 23 Celsius. Getting really close to freezing point of water.
Wow. At what pressure?
Still very high, 170 to 190 gigapascals. But that 250 to 260 K TC is the highest confirmed, reproducibly verified critical temperature we have to date.
So these superhydrides, as they're called, HS, little heroes, they show near-room temperature superconductivity is real, scientifically speaking.
Undeniably real. And there's a common feature emerging in these materials.
What's that?
Their structure. They often form these beautiful, highly symmetric cage-like structures called clythrates.
Clythrates, like cages.
Yeah, the hydrogen atoms form cages that enclose the metal atoms. In LAR, for instance, you have these cages made of 32 hydrogen atoms surrounding each lanthanum atom.
And that structure is important.
It seems crucial. This rigid, symmetric hydrogen sublattice appears to be perfect for hosting the very high-frequency lattice vibrations, the phonons, needed for strong electron-phonon coupling and thus high TSE, just like BCS theory would suggest.
So it all fits the phonon picture, just pushed to the extreme by hydrogen and pressure.
Largely, yes. It's a triumph for that side of the theory.
Okay, but we keep coming back to the pressure. 150, 190 gigapascals. That's what, 1.5 million times atmospheric pressure?
Roughly, yeah. Achievable only in tiny diamond anvil cells squeezing microscopic samples.
So completely impractical for, power lines or MRI magnets.
Utterly impractical for applications right now. It's fantastic fundamental science, but you can't build technology with it yet.
Which means the big challenge isn't just getting T to RE10, it's getting the pressure down.
Right.
Way down.
Exactly. That's the major focus now for the hydride field. Can we stabilize these high TC structures at pressures closer to ambient?
How are people trying to do that? Sounds like finding a needle in a haystack.
It is a huge challenge, and it's really pushing the boundaries of materials prediction. A lot of effort now is computational.
Using computers to design materials.
Yes, using things like density functional theory, DFT, and algorithms specifically designed for crystal structure prediction, CSP. They can screen thousands of possible chemical compositions and structures virtually.
Trying to find combinations that might be stable and superconducting at lower pressures before doing the difficult experiments.
Precisely. And a few key strategies are emerging from this. One is alloying or doping, adding a third or fourth element into the mix.
Like making ternary or quaternary hydrides.
Right. The hope is that the extra elements might help prop open those hydrogen cages, stabilizing the superconducting structure without needing quite so much external pressure. People are looking at things like mixing lanthanum and yttrium, or systems like lithium-magnesium hydride, liter, and geotra.
Interesting. Any other strategies?
Another idea is metastability, or pressure quenching.
Quenching, like cooling really fast.
Yeah. You synthesize the material under high pressure where it is stable and superconducting. Then you rapidly cool it way down while still under pressure and then release the pressure.
And the hope is?
The hope is that the low temperature freezes the high pressure structure in place so it persists even after the pressure is removed. A bit like how diamond, which forms under high pressure deep in the earth, stays diamond at the surface.
So maybe the high TC ice on hydride could be quenched to exist at ambient pressure.
It's a long shot. Hasn't worked yet for these hydrides, but it's theoretically possible. The big picture here, though, is this tension.
Tension.
The very structures, these dense hydrogen clathrate cages that seem necessary for high TC via the phonon mechanism, also seem to intrinsically require high pressure for stability.
Ah, so the thing that makes them good superconductors also makes them need high pressure.
It seems that way. The grand challenge, the key insight needed perhaps, is finding a way to break that link, to get the high-frequency phonons without the crushing pressure.
A massive material science puzzle.
Truly.
Okay, so that's the high-pressure frontier. Validated, progressing, but facing this huge pressure hurdle now.
Yeah.
Let's talk about the other side of the coin. The ambient pressure claims.
Right, the cautionary tales. These are important, too, for understanding the process of science.
Probably the biggest recent one was LK99. That blew up online last summer, 2023.
It really did. Preprints came out from a South Korean team claiming superconductivity in this lead-copper apatite material, and the claims were extraordinary.
What exactly did they claim?
Room temperature, ambient pressure superconductivity. Specifically, a sharp drop in resistance starting well above 100 degrees Celsius near 127 C, and some videos showing partial levitation of small flakes over a magnet.
Room temperature and ambient pressure. That's the absolute jackpot.
Which is why it went viral. It triggered this unprecedented global rush to replicate the results. Scientists everywhere sharing progress, failures, data, often in real time on social media. It was quite something to watch.
Was there any reason, theoretically, to think it might be true?
There was a tiny sliver. Some initial calculations, DFT again, suggested the possibility of flat bands near the Fermi level in LK99's electronic structure.
Flat bands. What does that mean?
It's a feature where electrons basically have very little energy change when their momentum changes. This can make them act heavy and interact very strongly with each other, which is sometimes thought to be favorable for high-temperature superconductivity.
So just enough theoretical plausibility to fuel the fire.
Just enough. But the experimental replication efforts quickly poured cold water on it. Lots of labs synthesized LK99 samples.
And what did they find?
Overwhelmingly, no superconductivity. The material was generally found to be a resistor or maybe a semiconductor, certainly not zero resistance.
What about the levitation? The videos looked compelling.
The partial levitation wasn't consistent with a true Meissner effect. Proper superconductors show strong diamagnetism, completely expelling the field. The LK99 effects were weaker and could be explained by ordinary ferromagnetism, likely from impurities, or just standard diamagnetism, which many materials show weakly.
So not the real deal.
Mm-hmm.
And the sharp resistance drop at 127C.
That turned out to be the smoking gun. Several groups identified a common impurity in many of the LK99 synthesis attempts. Copper, I, sulfide, QS.
Copper sulfide.
Yes. And guess what? QS undergoes a structural phase transition at almost exactly that temperature, around 104, 127C, depending on specifics. And associated with that transition is a sharp drop by orders of magnitude in its electrical resistivity.
So an impurity was mimicking the signature they claimed was superconductivity.
Precisely. It wasn't superconductivity at all. It was a known phase transition in a contaminant. Once groups managed to make very pure LK99 crystals, they found they were transparent insulators. Game over.
Wow. So LK99 was basically a case of maybe poor materials characterization, misinterpreting artifacts?
Exactly. A failure of careful materials science and data interpretation. But the positive side is how quickly the global scientific community, working openly and collaboratively, corrected the record. That rapid, massive replication effort was science working as it should.
Okay, so that's LK99. But there was another series of controversial claims, the Dias saga.
Right, involving Ranga Dias and his group. This had a couple of chapters.
What was the first one?
In 2020, they published a paper in Nature claiming superconductivity in a carbonaceous sulfur hydride, CSH. The temperature was pretty good, 15 degrees Celsius, near room temp.
Right.
But the pressure was enormous, 267 gigapascals, even higher than Lahiro. And more importantly, serious questions were raised almost immediately about the data, particularly the magnetic susceptibility measurements used to show the Meissner effect.
What was wrong with the data?
Critics argue that the way the background signal was subtracted wasn't standard and seemed to artificially create the apparent signal of magnetism being expelled. The raw data didn't look convincing.
So data analysis issues. What happened?
After a lot of back and forth and investigation, Nature eventually retracted that CSH paper in September 2022, citing unresolved concerns about the data presentation and analysis.
Okay, retracted. But then the same group came back with another major claim.
Yes, in March 2023, again in Nature. This time it was a nitrogen-doped lutetium hydride, LuHN. And this claim was even more spectacular.
Why? What did they claim for LuHN?
Superconductivity around 21 degrees Celsius room temperature, but at a pressure of only 1 gigapascal.
1 gigapascal.
Yeah.
That's still high, but vastly lower than the hundreds of GPa for the other hydrides. Low enough that many more labs could potentially check it.
Exactly. 1 GPa is achievable in different kinds of pressure cells, so replication attempts started quickly again, and nothing. Nobody could reproduce it. No other lab found superconductivity in LuHN near room temperature and 1 GPa.
So failed replication again.
Yes, but this time it went further. In a pretty dramatic turn, a majority of the co-authors on the original LuHN paper formally requested that Nature retract it.
The authors themselves asked for retraction. Why?
They stated that the published paper did not accurately reflect the actual experiments performed, the material characterization, or the data processing. Subsequent investigative reports detailed specific allegations of data fabrication and misrepresentation concerning things like the actual pressure measurements and even the elemental composition of the samples.
Wow, that's much more serious than misinterpreting an impurity signal.
Absolutely. This wasn't just about interpretation. It raised fundamental questions about research integrity. Nature retracted the LuHN paper in November 2023.
So the Dias saga represents a different kind of scientific failure mode.
It does. If LK99 was about getting the science wrong but being corrected by open replication, the Dias retractions point towards issues of scientific conduct, ultimately being addressed in part by whistleblowers from within the research team itself.
These are tough stories, but important ones. What's the takeaway? What does this all mean for how we evaluate claims going forward?
I think these episodes, while painful, have ultimately reinforced the vital importance of rigorous standards of evidence in this field. The old saying holds true. Extraordinary claims require extraordinary evidence.
And that evidence needs to be multifaceted and consistent?
Absolutely. It's not enough just to see a drop in resistance. You need to demonstrate true zero resistance, measurable zero.
Okay.
You need to show an unambiguous Meissner effect, clear expulsion of magnetic flux, ideally shown with different types of magnetic measurements, zero field-cooled and field-cooled that give consistent results.
Right.
You really should see a thermodynamic signature too, like a sharp jump in the material's specific heat capacity right at the critical temperature. That's a hallmark of a true phase transition.
So resistance, magnetism, thermodynamics, all pointing to the same transition temperature.
Exactly. Consistency is key. And then the ultimate acid test, reproducibility. Can other independent labs following the recipe make the material and confirm all those signatures at the same temperature?
Reproducibility, the bedrock of science.
It truly is. The scientific process, with its cycles of claims, scrutiny, replication attempts, debate, it can be messy, sometimes slow, but it's designed to be self-correcting. These recent cases, in their own way, show the system eventually working.
Okay, so we've covered the high-pressure successes and the ambient pressure controversies. What about those unconventional superconductors like the cuprates? Where does that research stand?
Yeah.
Are they still relevant to finding RTS?
Oh, absolutely relevant. They represent a completely different route, potentially, one not relying on the extreme pressure phonon mechanism.
Remind us about the main families again, cuprates and DAN.
Cuprates, discovered 86, still hold the record for highest TC at ambient pressure, about 133 K for a mercury-based cuprate, maybe up to 164 K under moderate pressure. And the iron-based superconductors, the FSCs, discovered around 2008, their TCs are lower, up to about 55 K, but they added another whole class of materials to study.
And the key thing about both families is that phonons aren't thought to be the pairing glue.
That's the general consensus, yes. Their behavior is really hard to explain with simple electron-phonon coupling. Instead, the evidence points towards magnetism.
Magnetism.
How does that work? Well, both cuprates and iron-based superconductors have parent compounds, the materials you start with before doping them to make them superconducting, that are typically usually antiferromagnetic.
Yep.
Superconductivity seems to emerge right when you suppress that magnetism, but not completely kill it. It's like superconductivity and magnetism are competing, but also intimately related.
So the idea is that fluctuations of the magnetic order, sort of magnetic wiggles or waves.
Exactly, spin fluctuations. Those might be providing the attractive interaction, the glue, that pairs up the electrons in these materials. It's a quantum mechanical dance between magnetism and superconductivity.
That sounds incredibly complex.
It is, and understanding that interplay is a huge focus. It's about navigating these competing quantum phases of matter.
And there's this other weird thing associated with them, right? This strange metal state.
Ah, yes, the strange metal. That's often the normal state you find above the superconducting transition temperature in many of these unconventional materials.
And why is it called strange?
Because its properties are, well, strange. They defy our standard theories of how electrons should behave in metals. The most famous is its electrical resistance.
What does it do?
It increases perfectly linearly with temperature, just a straight line, often over a huge temperature range. Rho is proportional to T.
Why is that strange? Don't metals normally increase resistance with temperature?
They do, but usually it follows a more complicated pattern, often like T squared at low temps, than bending over. This perfect linearity is bizarre. It implies electrons are scattering off something incredibly efficiently, almost as fast as quantum mechanics physically allows. It's sometimes called Planckian dissipation.
Scattering as fast as possible.
Yeah.
Like the electrons lose their individual identities.
Kind of. It breaks down our usual picture of electrons as well-defined quasi-particles moving through the lattice. It suggests the charge carriers might exist in this highly entangled collective state, almost like a turbulent quantum soup.
A quantum soup. And this strange metal is the state out of which high-temperature superconductivity emerges.
That's what's so fascinating. It seems this maximally chaotic state might be the necessary precursor, the parent state, for unconventional superconductivity. If we could crack the code of the strange metal.
We might find the secret recipe for even higher TC, maybe even room temperature.
That's the hope. Understanding the strange metal is considered one of the biggest challenges and potentially biggest opportunities in condensed matter physics today. It might hold the design principles we're missing.
Wow. Okay, so unconventional superconductors, magnetism, strange metals. Any other frontiers we should touch on? What about topological superconductivity? Sounds even more exotic.
It is. Topological superconductors, or TSCs, are a newer area that combines superconductivity with ideas from topology, the mathematical study of shapes in spaces that don't change when stretched or bent.
How does topology apply to a superconductor?
It relates to the quantum mechanical wave functions of the electrons. A TSC has a superconducting gap, like any superconductor, but its electronic structure also has a non-trivial twist or topology. This combination is predicted to lead to some really weird and wonderful effects, such as hosting Majorana fermions at their edges or in the cores of magnetic vortices.
Majorana fermions. Those are the particles that are their own antiparticles.
That's the ones. Finding definitive proof of them is still ongoing, but they're theoretically predicted in TSCs. And the big practical interest here is
Quantum computing.
exactly. These Majorana modes are thought to be inherently robust against local disturbances, making them potentially ideal building blocks or qubits for fault-tolerant topological quantum computers.
So the drive for TSCs is largely about quantum computing, not necessarily higher TCs.
Primarily, yes, although there are some theoretical ideas connecting topology, especially those flat bands we mentioned with LK99, to potentially enabling strong interactions and maybe very high TC in certain topological materials. It's an area where fundamental physics and potential applications are tightly linked.
Okay, so we've journeyed from the basics through the high-pressure successes, the ambient pressure stumbles, into the weird world of unconventional and topological materials. As we wrap up this deep dive, what's the big picture?
I think the big picture is that the quest for room temperature superconductivity is as active and, frankly, as challenging as ever. It's been shaped recently by both really solid monumental successes and some quite public, sobering failures.
The successes being the high-pressure hydrides.
Yeah, definitely. Lahar hitting 250, 260 Kelvin is undeniable proof that near room temperature superconductivity is physically possible, at least via the phonon mechanism pushed to its limits. That's a huge milestone.
But with the giant asterisk of pressure?
Exactly. That immense pressure remains the fundamental barrier to any practical application of those materials. So the focus there is now squarely on rational materials, design computation, doping, maybe metastability, trying to find ways to lower that pressure requirement.
And the ambient pressure claims. LK99, the dias materials.
Those have served as critical, if painful, cautionary tales. They stress-tested the scientific method in the modern era of instant communication. They underscored the absolute necessity of rigor, transparency, and independent verification.
And reinforced the standards of evidence needed.
Absolutely. Zero resistance, clear Meissner effect, a heat capacity jump, all consistent, and ultimately reproducibility by others. Those are the non-negotiables now.
So looking ahead, where does this leave us? If high-pressure hydrides are locked away and ambient claims haven't panned out, what's the most promising path forward?
That's the multi-billion-dollar question. It feels like getting to a practical ambient RTS might require more than just optimizing the known pathways. It might need a real conceptual leap.
A leap based on.
Perhaps a deeper understanding of the unconventional superconductors. Cracking that strange metal puzzle, figuring out how magnetism and superconductivity really dance together. Maybe finding new pairing glues entirely. Or perhaps harnessing some of the novel physics emerging from topological matter. We might need new physics, not just new materials.
So the dream is still alive, but the path might be even twistier than we thought.
It seems that way. The quest continues, but maybe now on a slightly firmer scientific footing. We're guided by the validated successes like Lahar, but also sobered and made more rigorous by the hard lessons learned from the failures.
It really makes you wonder, maybe the key isn't just about finding the right combination of atoms in a lab. Maybe unlocking this century-old dream requires us to unravel the very fabric of quantum reality in ways we're only just beginning to comprehend. What stands out to you from this deep dive?